Thermal expansion. It happens to everything. It happens everywhere. Now this is a bridge, and this is a roof, and these are jars. Now, what do any of these things have anything to do with each other? Well, thermal expansion. So, what is thermal expansion? Well, what's expansion? It's something getting larger. Thermal comes from a Greek word meaning heat. Now, every material in the universe expands upon heating. Just some to more extent than others, depending on the properties of the substance. But the real question as a scientist is, why does thermal expansion occur? Well, look at these two substances. One is hot and one is cold. The hot one has lots of energy in its particles, in its atoms, and the colder one has less energy. Look at this cube that we are going to heat up now, and its atoms are there, its particles are there. And as we heat up the object, the atoms get more and more energy, and they start to vibrate more and more, and they start to space out, and now they are expanding. Now I'm going to show you an experiment of a ball and a ring. So this is a classic experiment that we perform to show thermal expansion. We have a sphere and a ring, and as you can see, we're going to push this ball through the ring, and it's going to fit here. It's brass alloy, it's going to fit. It fits straight through. We're going to heat this ball up, give it some energy. The particles are going to gain some energy, and they're going to expand. They're going to separate from each other. And as you can see now, we're going to try to put it through the ring, and it doesn't fit because the brass is expanded. The brass ball expanded.
It is an experimental fact that almost all materials expand when heated and contract when cooled. As thermal energy is absorbed, the vibration of the molecules that make up the body is increased. The forces created by increases and decreases in molecular vibration are an interesting field of study for physicists and engineers. In many cases, the magnitudes of the forces involved can be astounding. To examine these forces, an iron bar will be heated and cooled while the impact of the force generated is observed. The iron bar is designed to rest in a sturdily constructed fixture that allows one end of the bar to be clamped in a stationary position. The free end of the bar is equipped with an open loop that extends beyond the stop blocks protruding from the fixture. To heat the iron bar, a 4-flame burner assembly is lit and a supporting grate is put into place. The bar is then located directly over the flame so that it receives the maximum amount of thermal output from the burners. Throughout the heating process, the bar expands as the iron molecules increase their vibrational amplitude and frequency. After the bar has been heated to several hundred degrees Celsius, it is laid into the fixture, and an iron rod is fitted through the open loop at the end of the bar. The back end of the bar is then clamped down, fixing its position. As cool water is poured over the iron bar, it is instantly vaporized, removing thermal energy from the bar. The resultant cooling of the bar reduces the energy level of the vibrating molecules, and the iron bar begins to contract. As the iron bar contracts, the rod becomes trapped between the iron bar, which is exerting a horizontal force in one direction, and the stop blocks of the fixture, which are exerting an equivalent force in the opposite direction. As the cooling and contraction continue, slight bending in the iron rod becomes evident. In fact, the iron rod is no match for the forces of thermal contraction and finally gives way altogether. As a material expands with heating, the amplitude and frequency of molecular vibration increases. The result is thermal expansion. When cooled, the molecular vibration decreases and the material contracts. The forces generated by the summing up of the individual molecular contractions can be quite significant. For example, the force needed to snap the iron rod shown in the experiment is approximately 4,000 newtons, a force roughly equivalent to that needed to lift a 1,000-pound mass.
Now here's another experiment. We're going to take a Bunsen burner and we're going to use this Bunsen burner to get heat, right? Just like the other experiments. And so we're going to take now a metal strip made out of two different metals, copper and iron. It's called a bimetallic strip because there's two different metals in it. And when we heat up this strip, what happens, we notice that it curves. It starts to bend. The reason why it bends is one metal actually expands more than the other. One increases in length more than the other. So the one that has the greater length is going to be the one on the outside, curving it inwards, and the one on the inside is the shorter one. So the one on the top here in this case is the one that's expanding less, and the one that's on the bottom is the one that's expanding more under heat. And when we cool it, you notice that it actually returns to its original position where it's flat and not curved anymore. And so this is the essence of thermal expansion. On heating, we get an extension in length, and when we have two different materials, you have difference in extensions in length. So you when they attach, it actually curves it, and there's usefulness in this. We actually use this in things like temperature alarms, fire alarms and such, because when it bends, what you can do is you can attach it to an electric contact. So when it curves enough, it will close the circuit and cause a sound to go off, a siren to go off. And there's many different uses of these bimetallic strips, like in refrigerators to control temperature and such things. It's very reliable, and so it's very useful. Now back to our bridge, our roof, and our jars. When you have a bridge in an environment where there's fluctuating temperatures, the materials that make up the bridge can expand and contract. And so you have to make provision in the design of the bridge for this expansion and contraction. So sometimes you see in bridges that there's teeth in these bridges that come closer together when expansion occurs and go further apart when contraction occurs. And so cars can still pass over, and so the bridge just works well. And when you have roofs that experience temperature fluctuations, they can expand and contract, and they creak, they make noises. And when you have a jar that's very tightly closed, you can put hot water over it, and the lid of the jar will expand, and now you can open it easier. So very useful stuff. So this here is another experiment with a bottle full of air and a balloon on top that's completely deflated. There's some boiling water and some ice. So we're gonna put the bottle of air in boiling water to heat up the air. The air is gonna get hot, and what we're gonna see is that the air is gonna expand into the region where the balloon is, and it's going to inflate the balloon. This is the gas expanding. This is thermal expansion as it pertains to gases. You can see here the little smiley face man, balloon man, just expanded. He inflated because the gas expanded because it was hot. And so we're gonna cool him down now. We're gonna cool down the air in the bottle, and you're gonna see right now that smiley face man is going to deflate. So we watch as it cools, and bit by bit, wow. Look at that. We have smiley face man deflated because the air it contracted upon cooling. Now for gases, we can account for this type of behavior with the gas laws. Charles' law is the law that deals with what we just saw. It's all about volume and temperature. So if you have a gas that's of a fixed mass and you were to increase its temperature, the volume would increase in proportion. And if you decrease this temperature, the volume would decrease in proportion. But you have to keep pressure constant. And the reason why this occurs is because as the temperature increases, the particles gain more energy and they move about more violently and they separate more. So the volume increases. And as you heat a gas, as Charles did in his experiments with hot air balloons, he was trying to investigate how hot air balloons work. He noticed that the volume increased as you heat the balloon up, the air in the balloon up, and as you cool it down, the balloon actually decreases in size. So he was experimenting to figure out how hot air balloons work, because they didn't know how exactly they worked at the time. So this Jack Charles guy, probably butchered his name, he was French, he was a French scientist. He came up with the first hydrogen hot air balloon, and he went on the balloon himself and made the trip in the air and back down. And so his law states that for a fixed mass of gas at constant pressure, volume is directly proportional to temperature. And in equation form, that's V is equal to some constant times temperature, where V is the volume and T is the temperature measured in kelvins, and K is some proportionality constant which we use. So if you divide the volume by the temperature, you're going to get that proportionality constant. Quick maths. But take a look at this. This here is a graph, same graph of volume versus temperature, same Charles' law graph, right? Scientists of the day were looking at this graph when they did the experiments, and they thought, what would happen if I bring the line back down? What would happen if I bring it back all the way to the point where volume becomes zero, essentially making the gas disappear? So is there some point where I bring the temperature so low that the volume becomes so small that it essentially disappears? That point is called absolute zero, temperature at which gas or any substance reaches zero volume, and it reaches very low activity, zero energy, zero everything, right? And this happens at minus 273.15 degrees Celsius, approximately minus 273 degrees Celsius. That point there is a zero on the Kelvin scale. That's a 0 point. So it goes up from there to 1 Kelvin, 2 Kelvin in the same proportion as Celsius. So it's essentially the same unit, the same thing as the Celsius scale, except it starts at an earlier point, at that minus 273 point. It takes that as 0. So 0 degrees Celsius in the Kelvin scale is actually 273 Kelvin, right? So that's how that works. So yeah, awesome, right? So here we have a balloon. We're gonna make some change to this balloon. We're gonna heat it up, the air inside the balloon, and the volume is gonna change. But we know from Charles' law, the equation that we have, V on T is equal to some constant. That constant is not gonna change. So the first instance, V on T, is equal to the second scenario, V on T. So then they're going to equate V on T, V1 on T1 is equal to V2 on T2. So we're gonna look at this example here where we have a hot air balloon as a volume initially of 2800 meters cubed, 99 degrees Celsius, and we're asking what is the volume if the air cools to 80 degrees Celsius. So we have an initial volume, a final volume, an initial temperature, a final temperature. So we're going to use Charles' law. V1 on T1 is equal to V2 on T2, and we have to convert everything to Kelvin in terms of temperature for everything to work out well with these equations. So we just did some questions on that. So Kelvin is whatever the Celsius value is plus 273. In this case, we're gonna be a little extra and be exact with the 273.15. So the T1 ends up being 372.15 and the T2 ends up being 353.15 when you add the 273.15. And so what you have is V1 on T1 is equal to V2 on T2, where we substitute everything in. 2800 on 372.15 equals V2, which is the unknown, on 353.15. So that's V1 on T1 equals V2 on T2. And so what we're gonna do, we're gonna multiply both sides by 353.15 to get V2 by itself on the right side. So you see everything there, and then of course the 353.15 cancels out to give V2 by itself on one side, and we calculate it to be 2,657 meters cubed. So here we have another question about another balloon, a gas in a balloon. At 0 degrees Celsius, a gas occupies 22.4 liters. How hot must the gas be in Celsius to reach a volume of 25 liters? So we're using Charles's law again, because we have initial temperature, initial volume, and final temperature, final volume. V1 on T1 equals V2 on T2, and we have to convert the temperatures to Kelvin again. Same thing, Celsius plus 273.15. That's gonna give us T1 as 273.15 because this is 0 plus 273.15, and then the T2 is what we're trying to find out. So the 22.4 divided by, that's the V1 on the T1 of 273.15 is equal to 25 liters divided by T2. So we're gonna solve for T2 now. So we cross multiply here to get 22.4 multiplied by the T2. 22.4 liters multiplied by the T2 is equal to 273.15 times the 25, right? And so if we take T2 as the subject of the equation, we get 273.15 multiplied by 25 divided by 22.4 would be the answer, and that works out to 304.9 kelvins. But if we look here, we wanted to find out how hot must the gas be in Celsius. So we're gonna have to convert the temperature back to Celsius. So we're gonna Kelvin minus the 273.15 gives us the Celsius, 31.7 degrees Celsius. So this is Charles' law. V equals some constant times T, right? So that's how life works with gases with respect to volume and temperature. So Charles' law, if you were to put it in an official sentence, I like to call it the hot air balloon law, because that's what Charles was experimenting with and was trying to figure out about. So volume, think about the hot air balloon, and you're heating some air with fire, right, or whatever it is, right? And the air is increasing in volume, but it's the same fixed mass, it's the same amount of mass, but it's increasing in volume. And what does that do to density? It is going to decrease density, because density is mass over volume. Volume increases, mass stays the same, then the density is going to decrease. And what does that mean? If we have air that's hot, comparing to its surroundings, the hotter air is going to rise. Okay, they say hot air rises. It's because it's less dense than cold air, right? Or room temperature air or whatever. So the volume of a fixed mass of gas is directly proportional to its absolute temperature, meaning temperature in kelvins, right? Absolute meaning starting at from the actual 0 point, right? Provided that the pressure of the gas is kept constant. Important here, we're keeping the pressure constant. If we don't keep the pressure constant, you can't apply Charles' law. Charles' law is not going to work, right? So Charles' law applies for where you have pressure not changing and mass is the same. It's a fixed mass. So officially, volume of a fixed mass of gas is directly proportional to its absolute temperature, provided the pressure of the gas is kept constant. So we have here the representation of this. V is proportional to T. V is some constant times T, and so if we rearrange this equation, V on T is equal to some constant, and that constant doesn't change. So before and after, if you change a gas, if you add some heat or you change the volume, whatever it is, the constant remains. So you can use that constant to your advantage, so that you know that V on T in the first instance is equal to V on T in the second instance, right? Before and after. So V1 on T1 is equal to V2 on T2. So that's how it works. So Charles' law. Give it up for Charles' law, the hot air balloon law. Look at that. Increased pressure means decrease in volume of the air in the balloon. There we have it. Decrease in pressure leading to an increase in volume of the air in the balloon. So when you have a Coke can and you open it, all the gas bubbles that are in the beverage increase in volume once you open it to the air. So they kind of spew out, right? And so this is why that happens. So that right there was Boyle's law in action. So Boyle's law is all about fixed mass of gas where you vary pressure and or volume, and it's about the relationship between that pressure and the volume. So you decrease volume, pressure is going to increase. You increase volume, pressure is going to decrease. So they're inversely proportional, and that's because if you give them a smaller space, all the particles of the substance, a smaller space to act within, they're going to bombard on the surfaces around them more often. So here you're going to see that we're going to push down this piston, and you're going to see that these particles that make up the gas are going to hit the walls of its container more often, and that results in a higher pressure, right? So there's a lower volume within which the gas can act, can exist, and the pressure would increase. So now we're going to increase the volume. We pull up the piston, we're increasing the volume, and now the pressure is going to decrease because they have a much larger space to act, so they bombard against the surfaces much less often. So this guy is Robert Boyle. He's the guy responsible for publishing this law about pressure and volume, the relationship between the two. So he discovered, or rather he published, that it was discovered by people because it wasn't originally discovered by him. Fun fact. But pressure is inversely proportional to volume. So pressure is proportional to 1 over volume. Pressure is equal to some constant times 1 over volume. So P times V, when you rearrange the equation, is equal to some constant K. So if you have a gas and you make a change to it, it's in some container, you change the volume, you change the pressure. Because we know that there's this equation, PV is equal to some constant, then you can see that PV before is equal to PV after. So P1 times V1 is equal to P2 times V2 because of that constant, right? Stays the same, it's constant. So let's say you have a tire with a volume, a known volume of 11.41 liters, right? That's a unit of volume, and then we have the tire is reading at the tire gauge 44 psi, pounds per square inch. That's pressure, right? It's a unit of pressure used with tires. So what is the new tire pressure if you compress the tire and its new volume is 10.6 liters? So we know we can use Boyle's law because it's pressure and volume involved, and we are going to use the equation P1 V1 equals P2 V2 because PV before equals PV after. So when we write down all the values, we see that, you know, we have P2 as the unknown, so we're gonna want to rearrange to be able to get P2 as the subject of the equation. So we move the 10.6 liters to the other side, we divide by 10.6 on both sides, so it cancels out, and now we're gonna find the answer. The answer turns out to be 47.36 psi, which is approximately 47 psi, right? So let's say we had a syringe of volume 10 cubic centimeters. So this CCS stands for cubic centimeters, apparently, in this case, but don't use that in exam, right? It's cm to the 3 cm cubed, right? Anyway, the pressure is 1 atmosphere. If you plug the end so that no gas can escape, that is fixed mass of gas, and push the plunger down, what must be the final volume to change the pressure to 3.5 atmospheres. So we know we're using Boyle's law because pressure and volume involved. P1 V1 equals P2 V2. So we plug the numbers in. 1 atmosphere, that's P1 times 10 cm cubed, that's V1 is equal to 3.5 atmospheres times V2, and we bring 3.5 across to get V2 on one side of the equation, and we're gonna find that V2 final answer is 2.9 cm cubes. That is how much volume is going to be. So that's Boyle's law for you. PV is a constant. P is inversely proportional to V, given that you have a fixed mass of gas at a constant temperature. So officially, Boyle's law involves pressure and volume. I like to call it the air spring law because that's what Boyle published his paper as. That was the title of his paper, the spring of air, because when you push down on air, if you push down on it and if you don't allow any to escape, it will push back on you like a spring. So that's why he called it the spring of air. So it's to do with pressure and volume. So the pressure of a fixed mass of gas is inversely proportional to its volume, provided that the temperature of the gas is kept constant. So we can represent that like P proportional to 1 over V, and so P is equal to some constant times 1 over V. If you rearrange, that's PV is equal to some constant. So that's Boyle's law for you. Very useful. So here we have another experiment, yet another experiment. We're gonna talk about something else now. We are gonna put this gas in this sphere container, and there's a pressure gauge attached to it, and we have a thermometer. We're gonna read the temperature, 100 degrees Celsius. We're putting it in a water bath. Right now it's 948 millimeters of mercury in terms of the reading on the pressure, and we're gonna now put it in some lower temperature water. Temperature is 51.5 degrees Celsius, and we see that the pressure responds, it changes, and it's lowered now to 838 millimeters of mercury. So the pressure actually decreased with the temperature decreasing as well. So we see that there's a proportionality there, a direct proportionality. So the law that applies here is called the pressure law. In some places they call it the Gay-Lussac's law, because it's some person that discovered this centuries ago, and that was his last name. So it talks about a gas. You have temperature and pressure directly proportional to each other. As temperature increases, pressure increases. As temperature decreases, pressure decreases. And this is because as you increase the temperature of a gas, the molecules are going to vibrate more violently, and they're going to hit against the walls of its container with larger force because they have more velocity. So the pressure is going to increase as temperature increases, and the pressure will also decrease if the temperature decreases. So there is a direct proportionality there. So it's this guy by the name of Joseph Louis Gay-Lussac and Guillaume Amontons. I butchered his name, sorry, foreign people from centuries ago. What they realized is that pressure is directly proportional to temperature for fixed mass of gas at constant volume, of course. So P pressure is equal to some constant times T temperature, right, where temperature is measured in kelvins. And so if we rearrange this equation, P on T is equal to that constant that we're talking about. So P on T is constant. So as we make a change in a gas in some container, in temperature and or pressure, we can use this equation P1 on T1 equals P2 on T2. I don't know if you see a pattern here, to be able to see things, how things work, and make equations and work out the equations and find the answers and stuff. So yeah, so let's imagine we have somebody comes up to us with a big canister of nitrogen gas, and it has a pressure, this person tells us, of 2000 psi, pounds per square inch, at 20 degrees Celsius. And they ask us what will be the pressure if you increase the temperature to 25 degrees Celsius. So we're going to use the pressure law. P1 on T1 equals P2 on T2. We have to convert to temperatures to Kelvin, of course, so that's Celsius plus 273.15. So the T1 comes out to 293.15, right, because 20 plus 273.15, and then T2 comes out to 298.15. And so we put the figures into the equation, and we rearrange to have P as the subject of the equation, right? So first we cross multiply, and then we divide, right? And so we get P2 as the subject of the equation, and the answer comes out as 2034 psi, 2034 psi approximately. Here's another example. We have a tank of gas, right, just like what people have in their house. At 10 degrees Celsius, the gas exerts 0.95 atmospheres of pressure, and this person who drops a tank in front of us asks us this question: at what temperature in Celsius will it exert at a pressure of 0.75 atmospheres? So we're going to use the pressure law. P1 on T1 equals P2 on T2. We're going to convert the temperatures to Kelvin, and then we're going to substitute everything in, plug all the values in, cross multiply, and make T2 the subject of the equation, because that's what we're trying to find. We get that T2 is 223.54 Kelvin. And so next what we're going to do is convert the Kelvin to degrees Celsius by minusing 273.15, and the final answer is minus 49.6 degrees Celsius. So that is the pressure law for you. The name of the guy is Gay-Lussac, that's his name. That's his last name, who discovered this law. P is proportional to T. And so officially the statement is that the pressure of a fixed mass of gas is directly proportional to its absolute temperature, provided that its volume is kept constant. Fixed mass, always fixed mass. And it's always pressure, temperature, and volume. So if you're varying pressure and temperature, then you have to keep volume constant. So P is proportional to T, and so P is equal to some constant times T, and so P on T is some constant. We can use that to figure things out. So yeah. Then we have this general gas equation. PV on T is equal to some constant. It's a combination of all the other gas laws, This is the combined gas equation, and so you can use this if you have a variance of more than one value. So if pressure and volume vary, or all three vary, right, you can have P1 V1 on T1 is equal to P2 V2 on T2, and work out things, and everything works smoothly, right? So yeah. So in summary, we covered thermal expansion. We showed the ball and ring experiment, right, where when we applied heat to the ball, it could no longer fit through the ring because the ball expanded. We showed the bar breaking experiment, which revealed the kind of force that the contraction and expansion of materials can yield, right? So it broke an iron bar which required many tons of force to be able to break, and that was just from cooling down an iron bar, an iron beam, right? So then we covered the balloon and air in a bottle experiment, which showed us how air expands when being heated. And so air is a gas, right? So it's not a solid, we're talking about a gas there. And we transitioned from there into the gas laws, which we saw Charles' law, which stated that V volume is proportional to T temperature at a fixed pressure, and if it's a fixed mass of gas, that is. Then we saw Boyle's law, which stated that P, pressure, is proportional to 1 over V, 1 over volume. In other words, pressure is inversely proportional to volume, right? For a fixed mass of gas is what we're talking about, and for Boyle's law, it must be at a fixed temperature for Boyle's law to hold. And then the pressure law, we checked this out and we saw that pressure is proportional to temperature, and that is for a fixed mass of gas, just like the rest, at a constant volume. And then we looked at the combined gas equation, which is a combination of all three these laws, equations for these laws. All three of them combined into one is the combined gas equation. PV on T is equal to some constant. PV on T is constant. Right, so that's what we covered. Hope you guys enjoyed, and that's about it.